It recognizes the thing. Hello. Oh yeah, look at that. All right, so I just have to make sure my clicker is clicking, and then I'll be really happy. All right, so here we go. And let's see. We may want to kill the lights. We'll find out when there's code up there. If you guys can't read it, I'll have someone kill the lights. But this is an interactive session. And in fact, well, we'll get there. First of all, some people say seeing is believing, but I'm here to show you it's not so. So take a look at this picture. You'll see the letters Cafe Babe. Anyone know why I picked those particular letters? Hex. What do they mean in hex? Where do you see those hex letters? Numbers, digits. Magic number in the Java class file. Very good. All right. So looking at these particular hex characters, it might look like they are tilted. You might see a slant. This one slanted left to right, right to left, and so forth. How many people see a slant? But it's not there. And I'm going to prove that it's not there. And the way I'm going to prove that it's not there is by putting translucent yellow ink on these letters slowly. Digital ink, of course. Now, do you believe they're not tilted? We remove the ink slowly, and you see the tilt again. But it's not there. I can prove it's not there. By the way, count it. Here's a whole diagonal and a half diagonal, whole diagonal, half diagonal, whole diagonal, half diagonal, not tilted. What about here, this one? Look at these dots. How many colors do you see for the little checkers on the board? Yell it out. 3. And how many are there? 1. And how do I prove it? I'm just going to dissolve the board away. 1 color. Bring the board back. You see all 3. So what's the point of all this? Well, the point is that things are not always what they appear to be. And I'm going to show you the same thing in code. I'm going to give you 8 little puzzles. Each one is a small program that appears to do something but actually does something else. And you're going to tell me, by show of hands, what it does. It's multiple choice. And participation is mandatory. And here's the deal. There are prizes, see, and you cannot win if you do not play. So it is in your interest to participate. You can even just guess, if you wish. And it's not all fun and games, because each of these problems carries with it a moral. So after we reveal what the program actually does, we will teach the lesson that program has to teach. And each of these will generally be able to save you from making one particular bug and perhaps advance your standing in tomorrow's competition. Who knows? So, on with the show. And by the way, the reason this is called Greatest Hits is because I've been doing this for 10 years or so. I've been doing these puzzlers, and these are ones that they've all been done before at some point over the last 10 years. So the dates here are when this problem first appears. If you know the answer, don't shout it out. If you don't know the answer, do feel free to sort of discuss amongst yourself. I'm going to go over each one. So this one here is a brain teaser. It says, if you pay $2 for a gasket that costs $1.10, how much change do you get? And before you all shout out, 90 cents. Remember, we're geeks, right? So we don't just say 90 cents. We write a program to answer the brain teaser. And here's the program. It's public class, and it's got one line in its main method. It just calls println of 2.00 minus 1.10. So the question is, what does this print? Does it print 0.9, losing the precision? Does it print 0.90, retaining the precision? Might it vary depending on whether you're using, like Oracle's VM or IBM's VM, or does it do something different? None of the above. So, by show of hands, how many people believe this one always prints 0.9, choice A? And raise them high enough that I can get a good count. So there are, I would say about 5, more actually 8, 10 of you are going for A. How many people say choice B? It remembers the precision. 5 of you. How many people say it can vary? About 15, 20. And how many people say none of the above? About 25. And those of you are right. It turns out that this one prints 0.89999999. And the reason is because decimal values cannot be represented precisely using binary floating point arithmetic. So let's take another look at the program. We have 2.00. What is the type of this value? Anyone? Double. Absolutely. Those are double literals. We're subtracting 2 double literals. The result is a double, and you can represent 2.00 exactly, but not 0.10, 1.10. Why not? Because a tenth is not representable as a sum of powers of 2. Halves, quarters, eighths, sixteenths. Why is that true? Anyone know? Why can you not ever represent a tenth exactly as a sum of powers of 2? Algebra, in particular, factoring. It's 1/2 times a fifth. A fifth is a prime number. It's the problem of incommensurable bases. So you lose. How do we fix it? Well, 2 ways. Either you use big decimal, right? Replace this with new big decimal of quote 2.00 dot subtract. It's ugly, but it works. And this one actually does keep track of the precision. So this one will print out 0.90. Or you could fix it this way. You could just say, let's use pennies. Let's print 200 minus 110. Do it all in integers, and it'll print out 90. Once again, it keeps track of the precision, but it doesn't print the decimal point for you. But these both get the correct answer. And this one runs much faster and is arguably less ugly. So what's the moral here? It's simple. Do not use float and double when you need an exact answer. They're great at doing approximate answers over a very wide range of magnitudes, from tiny to gigantic. But if you need exact numbers, as you do, for instance, when you're dealing with money, don't use floating point arithmetic. So, on to the next problem. This one kind of tries to fix the last one, and actually, it does better than that. It's a nicer program. We have the same brain teaser, but this time we're using big decimal, and I even do some sort of refactoring here, where I break it down. I introduce 2 local variables, 2 temporary variables here. We have the payment, which is new big decimal of 2.00, because we're paying $2 for the gasket, and the cost, which is new big decimal of 1.10, because the actual cost is $1.10. And then when I print it out, it's clear what I'm doing. I say payment.subtract cost. So it makes the big decimals look a little uglier. And that ought to solve it. So what does this one print? Does it print 0.9, 0.90, the same crap that the last one printed, or something else? Give a moment to think. Don't yell it out, but if you want to chat, that's okay. Yeah, would somebody be so kind as to grab me a water or something like that? Thank you. All right, because I have 8 problems, I will give you more time to think about the hard ones, but I should probably keep moving. Actually, by show of hands, how tired is everyone? If you're like really tired, raise your hand now. All right, so I'm going to keep this thing moving so you guys can get to bed, because also, you've got the competition coming up. I want you to be rested. So, on, let's vote. How many people believe that this one will print 0.9? About 10 of you. How many people say 0.90? About 15. How many people say same crap as last time? About 25. And how many people say none of the above? About 20, and you're almost all on this side of the room. And those one of you are correct. In fact, this one will print, wait for it, same number of 9s, and then a lot of very fancy stuff. So why is this printing all this disgustingly ugly stuff? In fact, why is it printing 2 lines of garbage? Well, the short answer is we're using the wrong big decimal constructor. Let's look again. See, we're passing, unfortunately, doubles to the big decimal constructor. And we're already dead. Garbage in, garbage out. In fact, this is what the spec for that constructor says. Translates a double into a big decimal, which is the exact decimal representation of the double's binary floating point value. So why did it print out something even uglier than the first program? Because big decimals are designed to be used with exact quantities. So instead of printing out what's called the canonical representation, sort of a reasonable representation of the value, it prints out the exact representation. How many bits are there in a double? 64. So that's what you're looking at when you look at this garbage. You're looking at 64 bits precisely translated into a decimal. That is the exact value of the thing that was represented as 0.8999 whatever last time. So how do we fix it? We use the right constructor. Use those quotes. And what can we learn from this one? Don't use the nasty big decimal of double constructor. Instead, use big decimal of string. You can't always do that, though. You can only use big decimal of string if you know the string at compile time, right? If you calculate the double, and then you need to turn it into a big decimal, what do? Well, then you have another method you can use called big decimal.value of double, which gives you a better result than big decimal of double. Big decimal of double gives you the exact result, which is never what you want. New big decimal of double gives you the exact result, which is never what you want. Big decimal.value of double gives you the result that you would get if you translated its argument to a string using the standard form. That is the canonical representation of the string, which is usually a reasonable version, and then turns that into a big decimal. So if you've got a non-constant value, use that. But this is really a lesson for API designers, okay? This is about making it easy to do the commonly correct thing. The idiot who designed big decimal didn't do that, right? He made it easy to do the wrong thing, he being me, of course. The thing is that if you want to make a big decimal, I should point out that it was the first thing I did when I arrived at Sun in 1997, so I didn't know what I was doing. But the point is that everybody, when they want to make something in Java, they tended, especially back then, to just reach for a constructor. New big decimal of 0.1, and sadly it doesn't do what you want. A good API designer makes it easy to do the right thing and hard, or better yet, impossible to do the wrong thing. Sadly, I failed in this case. What should I have done? Well, when do you actually want to get the exact value? When do you want to get the semantics of this constructor? Very rarely. The only reason you do this is because you're curious what the exact value of some particular double is. And if you find yourself, oh, by the way, okay, if you find yourself under those circumstances, then call this method. What should I have done? I should have, instead of using the constructor, I should have given it a name that made it clear what it actually did. What I should have done is made a static factory called big decimal.exact value of double. And then nobody would have used it accidentally. This causes real bugs in real programs. Don't do it. On. By the way, remember, you've got to keep track of how many questions you got right. I should have said that earlier. So hopefully you still remember for the first two. And the reason you have to is because on the honor system, we're going to be giving out these two fantastic prizes. They're wonderful books that everyone should have many copies of. And so what we're going to do after this is all over is ask you how many you got right, who got however many right, and whoever got the most right will get books, something like that. All right, this one is called A Big Delight in Every Byte. And it's a little more complicated than the first two programs, but it's not too complicated. It has a loop. It has a byte variable called b, starts at byte.min value, and goes all the way up to byte.max value. So it goes over all the byte values except one. Which one does it miss? Byte.max value. And why did I do it that way? Why didn't I say less than or equal to byte.max value? What would the program have done if I had said less than or equal to byte.max value? Yell it out. Infinite loop. Yes, indeed. The idea is that every byte value is less than byte.max value. You wrap around and it would just keep on going forever. So we cover every byte value except that one. And when we hit this particular value, if b is equal to 0x90, which isn't byte.max value, when we hit that value, we print joy. So my question to you then is, what does this program print? Does it print joy once when it hits this value? Does it somehow print it twice? Does it print joy, joy? Does it print nothing at all? Or does it do something else? Give you a moment to think. Whilst I grab some water. All right. So how many people believe that this one actually does print joy? And I should tell you that generally, at least one of the problems in these talks does what you think it ought, just because I don't want you to be able to rule out that answer. So how many people think it prints joy? 4 of you. How many people think joy, joy? Another 4 of you. How many people think nothing at all? About 25 of you. And how many people think none of the above? That is always a popular answer. In this case, 10 of you picked it. And in this case, majority rules. The 25 of you who said nothing at all are right. And the reason, don't you love these animations? So the reason is that the program is comparing a byte to an int, and the byte is promoted to an int with surprising results. Let's look again. We are comparing B is a byte, with 0x90. 0x90 is an int literal, and it is equal to positive 144. There are no byte values equal to positive 144. The byte values are between negative 127 and positive 128. That's byte min value and byte max value. So this guy here is not a byte value. Byte 0x90 is minus 112, and byte 0x90 unequal to 0x90. 0x90 is positive 144, and byte 0x90 is negative 112. Sad. So what's going on here? What's going on here is that we are comparing two unlike types. We're comparing apples to oranges, bytes to ints. So how do we fix it? Compare apples to apples or oranges to oranges. We want to compare bytes to bytes. We can just cast this 0x90 to a byte, and now they'll both be equal to negative 112, and it'll print joy. Or we can turn the we can turn the B into an integer, which we do by ending it with 0xFF. We're masking it. We are suppressing the sign extension that would otherwise occur. By the way, well, maybe I'll get to this in lessons, so hopefully it'll be there. So there's actually an even better way to fix this one, which is, why use this magic number at all of 0x90? Let's make a private static final variable called target and compare B to target. And now it won't compile at all. We'll get a nice error message saying possible loss of precision. You're comparing it into a byte, and because it won't compile, we know we have to fix it. So we do, and we actually put that cast up here, and we make the target a byte, and now we're comparing a byte to a byte. So I would argue that this is the best solution to this problem. So what can we learn from this one? A byte is not an int. Be careful when mixing primitive types. The compiler will convert them. It may not convert them in the way that you want. It's well specified in the Java language specification. It's called primitive widening conversions. But who remembers all that stuff? So always compare like-typed expressions, cast or convert one operand as necessary, and an easy way to get the compiler to remind you to do this is to replace that magic number with a properly named variable. One other thing that I should have had in this list, this is really a language flaw. Bytes should never have been signed in the first place. That's a big problem with Java. I was not there when that decision was made, but if I were, I would have tried to convince James Gosling to do otherwise. All right, this one's called Animal Farm. How many of you read Animal Farm at some point? Yeah, about half of you. I had to read it when I was in high school. So in Animal Farm, we find out that all animals are created equal, but some more equal than others. And it concerns pigs and dogs. So this program sort of loosely tests the conjecture that all animals are created equal. We have two variables. One is called pig, one is called dog. They're both final strings. Pig is initialized to length, 10, whereas dog is initialized to length, and then we append. The plus when used on a string does concatenation. We append pig.length. So what is pig.length? Well, it's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're appending 10 to length, and we get length, space 10. And then we print animals are equal, pig double equals dog. So the question is, what does the program print? Does it print animals are equal true, animals are equal false? Might it vary from run to run or VM to VM? Or does it do something else? I'll give you a moment to think about it. All right. So I hate to call for votes when there's all this chattering because it means people are thinking. This takes me back to the Khan Academy lecture. It's like I don't want to stop thinking and learning. So I'll give you another 5 seconds. Aren't I polite? And then we'll take the votes. I'd give you more time if it were earlier in the evening. All right. So how many people believe that this will print choice A? Animals are equal true. I think there's only one yes vote. How many people will go for choice B, animals are equal false? I got about half of you. I'm going to say that's like 30, something like that. How many people say it varies? A couple of you, 2 of you. And how many people say choice D, none of the above? About 20 of you, and some of you are very sure you're right. And in fact, you are right, and for the right reason. I heard you chattering. The reason is that the plus operator binds tighter than double equals. So if we look at this again, what we're doing is we're appending pig to animals are equal, creating animals are equal length 10, which is of course not double equal, that is identical to dog, because they don't even represent the same characters. That's awful, isn't it? So how do we fix it? Well, you might be tempted to fix it like this, right? You might just parenthesize it so that you get what you were actually aiming for in the first place. But this doesn't really do the trick, because this, while it might print animals are equal true, it might also print animals are equal false. Yeah, did I make it clear on the previous slide that it doesn't print either of the first two things? It simply prints false. It's just evaluating this double equals expression, and it ends up with false. So in this case, it'll print either animals are equal true or animals are equal false, depending on whether these two equal strings are identical or not. That is, the two strings both represent length colon 10, but there's no guarantee as to whether the string that is made here by appending the result of this Boolean test to this string is going to actually be the same object in memory as this one. This is interned. This may or may not be interned. Who knows? So there are no language guarantees as to whether this will print true or false. So what do we really want to do? Well, if it hurts when you go like that, don't go like that. Don't use double equals to compare your string. Use dot equals. And now we know that we are comparing the contents, the values of these strings. And in this case, they represent the same string, so it will print animals are equal true, just as it ought. And what can we learn from this? 2 things. First of all, use parens, not spacing, to express intent when it comes to order of operations, because the compiler pays attention to parens and ignores spacing. If you feel you have to use spacing to communicate to the reader of your program what it does, then for God's sake use parens instead, because the compiler doesn't give a damn about the spacing. And if you think you need to be clear to the programmer, that's a good sign that maybe you don't know exactly how it's going to be evaluated in the first place. Err on the side of too many parentheses. They don't cost anything. Use parentheses whenever there is any doubt. Also, you might see people occasionally write programs that use double equals on strings and actually work. Don't do that. Any program that depends on the compiler interning string constants is, if not broken, it will be soon. It's delicately balanced on running. It's a particularly dangerous hack, and here's why. The idea is that all you have is the assurance of the programmer that all strings are interned. But type-wise, an interned string and an uninterned string are both of type string. So the type checking that the compiler does gives you no assistance in ensuring that every string that gets compared is in fact interned. If you really want to intern your strings, make a separate type. Box it and call it interned string. And this way, if somebody passes in a string that's not interned, it won't even compile. All right. This one is called No Pain, No Gain. It was written by a friend of mine named Madbot McCloskey. He also writes novels, but anyway, that's for science fiction novels. That's for another day. So this one, it constructs a word using a random number generator in a string buffer, and it prints the thing out. So let's look at it in detail. We initialize the string buffer to null, and then we switch on random.nextInt of 2. So we generate a random number, and then depending on the value of the random number, we go to one of the 3 branches. If the random number gives us 1, we set the word, that is our string buffer, to be new string buffer of P. If we get 2, we set new string buffer of G. If we get something else, which is presumably 0, we set word to be new string buffer of M. Then we append A, we append I, and we append N. And finally, we print the word. So the question is, what words might this print? And by the way, there might be a hint in the title of the program. There might be, or I might be playing with you. So would it print pain, gain, or main, varies at random? Or would it print pain or main, varying at random, but never print gain? Or would it always print main? Or would it do something else? I'll give you a moment to look at this one, because it's kind of long and complicated. So I see a hand. I will answer any questions that anyone has at the end of the talk, but I want to keep it moving because I would really feel bad if, people didn't get enough sleep tonight on my account. All right. So I think people are coming to some conclusions. Is that right? All right. So how many people believe that this program prints pain, gain, or main, varies at random? Choice A. 1 person. All right. How many people believe pain or main, but no gain? About 10 of you. How many people believe main, always, every time? Oh, about 25 of you. And how many people think none of the above? About 10 of you. And those 10 of you are correct. This program always prints ain. It always prints ain. And the reason is, well, there are 3 separate bugs in this program. And depending on how many of them you spotted, you were led to different red herring answers. Let's take another look at the program. Okay? First of all, this is a fence post error. It should have been nextInt 3. That's the modulus. NextInt 2 always returns at 0 or 1, never 2. So if you wanted to return 0, 1, or 2, it should be random.nextInt of 2. And then these, why are those, give me a moment here. So there are no breaks is the next problem, right? No breaks. And that means what happens? Whether we go here or here, we fall through to this last case, and we assign new string buffer of M to word. Okay? And then we append A, I, and N. So it always prints main, right? And this is where you made the mistake. Here's the problem. What is this new string buffer of M thing? Well, sadly, string buffer has no constructor that takes a character. So what does it do? It does a primitive widening conversion of the character to an integer. And that is the capacity of the string buffer. But the string buffer contains no characters. It's kind of awful, isn't it? It really, all of these things, generally speaking, these programs point out some shortcoming in the language or its libraries. And we'll get to that in a moment. But anyway, so the string buffer that we get is empty. and then we append AIN, and we get AIN, and I ain't going to tell you again. So how do we fix it? Well, we fix the 3 bugs. First thing we do is we change it to with 3. Then we use double quotes to use the ordinary constructor that we all know and love that takes a string. And finally, we put breaks. So this program will print out pain, gain, or main with equal likelihood. But is it any good? Not really. It's ugly. It works, but it's not clear that it works. It isn't even clear what it's supposed to do. I claim that this is a better fix. Let's make a little helper method called random element that takes an array of strings. In fact, it could be generic. It could take an array of T. And then it returns an element of that array. And how does it get it? It says random.nextInt of a.length. So it actually takes the length of the array as the modulus. So if we added a new possibility to the string array, automatically the program would increment the modulus for us. And we choose an index that way, and finally we return the element at that index. Notice, by the way, that in order to make this work, I need a private static random number generator to use, and also it's not thread safe. Yes, it is thread safe. I forgot. It depends on the thread safety of random, and it turns out that random is thread safe. So strangely enough, this is actually thread safe. It's not terribly nice because if a whole bunch of different threads are using it, they're sharing a random number generator. They don't have to. It turns out that in order to make that run fast, as Click will tell you, random is a thread local. It turns out that every thread actually has its own random. No, I'm sorry. I'm dead wrong about that. That's not true for arbitrary randoms. It's only true for the one that's used by java.lang.math.random, the one that gives you floating point random numbers. Forget about that. Irrelevant. Anyway, so that's a nice program. And then how does the main look? We get an array containing main, pain, and gain, and we system.print out, random element of A. So not only is this correct, but it is clearly correct. And that is what you want. And what can we learn? First of all, use common idioms. This creating a string buffer using a character. You've never seen that before. And why not? Because it doesn't exist. If you must stray from the common path, look it up in the documentation and make sure that it actually works. In particular, if you're using something where you're passing a character and you're not sure if it works or not, remember that in Java, characters are not really a full-fledged type. A character is a half-assed int. It's a lot closer to an int than it is to a string. In fact, a character is a 16-bit unsigned int. That's all it is. In some cases, there are methods that treat them as actual Unicode characters, but otherwise, it's just a value, just an int. Watch out for fence post errors like these of 2 instead of 3 there, and watch out for sneaky puzzlers. There'll be a few more today. All right, 6 out of 8. And by the way, I think the last 2 are easy. So this is the last one that's, well, I shouldn't say they're easy. The last 2 are short. That would be a more charitable interpretation. All right, this one is called Histogram Mystery, and it's the longest and most complex program of the night. So what it's going to do is it's going to make a histogram based on the hash value of pairs of words. We have an array containing the words. It's a constant array, private static final array, words, and it contains 4 words. I recommend Polygene lubricants. Fair enough. And what do? Well, first we make a new histogram. The histogram is just an array of 5 ints. Okay? And we're going to use that to count how many of the word pairs have what hash values. So let's generate the word pairs. How do we do that? We have a nested for loop for string word 1 in words, for string word 2 in words. So we iterate word 1 through this array, I, recommend, and so forth. And inside that, we iterate word 2, and then we say pair equals word 1 plus word 2. This plus is doing string concatenation. So let's look at what pair is going to be. Pair will go I recommend, I polygene, I lubricants, recommend I, recommend polygene, and so forth. So how many times will we execute the body of this loop? 16, exactly right. because we have 4 pairs, and we're doing 4 pairs for the first word times 4 pairs for the second word. So it's like a table with 4 times 4 entries, or 16 word pairs total. And for each of the word pairs, we are going to figure out a bucket. And how are we going to do that? First, we're going to take the hash code of the word pair. The thing about hash code is it returns an arbitrary 32-bit integer. Could be positive, could be negative. But since we're going to use it to get an array index, we want it to be positive. So we take the absolute value, but that's not enough, because the array only has how many elements? Well, array.length, which in this case is 5. So we want to get an index between 0 and 4 exclusive. And the way we do that is we take the result of math.apps of the hash code, and we take it mod the length of the histogram. That's how we select our bucket. And then we increment the contents of that bucket. Histogram sub bucket plus plus. So each of the 16 trips through this loop, we're going to increment one of the 5 buckets. Which one? I don't know. I have no idea what the histogram is going to look like. All I know is that each of those word pairs is going to fall into one of the buckets. And then when we're all done, we're going to add up the contents of each of these buckets. We're going to set pair count, I suggestively named this variable, pair count, to 0. We're going to iterate over every value in the histogram. I call them freq because it's the frequency of that particular hash value mod 5. And we're going to increment the pair count by the contents of that histogram element. So we add up all the elements in the histogram, and then finally we print C plus pair count. So the question is, first of all, what are the contents of pair count after we've finished this loop? Sounds good. 16. Why 16? Well, because every one of the iterations of the loop has to increment one of the buckets. Which one, I don't know. But then when we add up all the buckets, since each of the 16 sort of lent its weight to one of the hash buckets, when we add up all the hash buckets, we're going to get 1 per iteration of the loop. So we're going to get 16, and we print C plus 16. So what does this program print? And by the way, just in case it helps you answer this problem, and I'm not saying it will, but just in case it does, I will tell you that the ASCII or Unicode value of capital A is decimal 65. I'm not saying you need that to answer this question, though. So I've got 4 choices for you. Choice A is it prints 83. Choice B, C16. Choice C, capital S. Or choice D, none of the above. But is a character like a string? Remember what I said about characters before? Character is just it's just a number. All right, it's time to take our votes, I think. Are you guys reasonably? You good? All right. So how many people think it prints choice A, 83? We've got about 15 of you. How many people go for choice B, C16? Nobody? I'll vote for it. They get lonely when nobody votes for them. I wouldn't want to like run off the slide so it's not there next time I give the talk. All right, choice C, the capital letter S, about 15 of you. That seems to be a popular number tonight. We come in 15s. And finally, choice D, none of the above. About, I'm going to say 10 or 12 of you. And those 10 or 12 of you are correct. It turns out that this program will always throw an array out of bounds exception. And as for the reason, well, it's a little bit complicated, but for starters, let me tell you that the absolute value operation is not guaranteed to return a non-negative number. There are circumstances under which it can return a negative number. And also, the mod operator it's not a true mod operator. It too can return negative numbers. It's actually a remainder operator. Let's take another look at the program. All right. The first thing I have to tell you is these words are not randomly chosen. They were very, very carefully chosen. It turns out that the hash code of polygene lubricants is equal to integer.min value. Hold that thought. Now, integer.min value is a very special value. It turns out that, how many of you people know all about 2's complement arithmetic? Raise your hands. Excellent. They teach you well here. So you all know that in 2's complement arithmetic, you have a different number of negative and positive values. Because how many int values are there in Java? Yell it out. 4 billion, roughly speaking. 2 to the 32. 2 to the 32 is an even number. And one of them is taken up with 0, leaving an odd number. And that means you cannot have the same number of negatives and positives. There has to be an odd man out. And that odd man out is integer.min value. It is its own negative. Negative integer.min value is equal to integer.min value. And I will prove it to you. How is integer.min value represented? It's got a 1 in the sign bit. Well, you tell me. How's it represented? And 1 in the sign bit and 0 is to the end. Let's negate it. We do that by inverting it. Now we have 0 in the sign bit and 1's to the end. And then you add 1. It carries, you get 0, carry the 1, 0, carry the 1, 0, carry the 1, until you get to the sign bit. 1 plus 0 is 1, and we are back where we started with 1 in the sign bit and 0's to the end. So negative integer.min value equals integer.min value. What happens when you take the absolute value of integer.min value? Well, if you look at the spec, it says that if the value is non-negative, it returns the value. Otherwise, it returns negative the value. If it's integer.min value, you're out of luck. So let's go back to our program. We take the hash code, which in the case of polygene lubricants is integer.min value. We take the absolute value, and we're still at integer.min value, a very large power of 2. And now we take the remainder when dividing that by 5. Here's the thing about remainder that you all should know. Do you know what the sign of the remainder is when you have a negative divided by a positive? Yeah, it's either 0 or negative. The idea is that it gets the sign from the numerator. Okay? So in this case, we're dividing a large negative number by 5. And what is the result? I think it happens to be negative 3, but that's unimportant. It's some negative number between negative 1 and negative 4. And any way you slice it, that's not a very good array index in Java. So when we try to increment that particular bucket, we throw the array index out of bounds exception, and we are dead. So we never get to the point where we add up the contents of the array. And by the way, I was messing with you here too, but I gave you a hint to that earlier tonight. I am adding a character value to an int value. Remember, characters are really a half-assed type in Java. They barely work as characters. Here we are doing an arithmetic operation on 2 integral primitive types, and because they're different, the narrower one is converted. It's called a primitive widening conversion to the larger one. That is, the character, which is an unsigned 16-bit quantity, is converted to, or it would be if we actually executed this line, to an int. So what is C as an int? Well, A is 65, and they're consecutive up from then. A, B, C, so 65, 66, 67, plus pair count. We said pair count would be 16 if we got that far, so it would be 67 plus 16 is 83. Yuck, that's disgusting. So how do we fix it? Well, the most important thing that we have to do is up here. What we have to do is we don't want to be taking the absolute value of this thing that could be integer.min value. So if we take the mod, the remainder, first, and then we take the absolute value, it's kind of hard to read in 2 lines, but you see I take the hash code, mod length, and then take the absolute value, we win. Why? Well, hash code could be anything from min value to max value. It could be a big negative number or a big positive number. Once I take it mod histogram length, it varies between -4 and +4, with 0 represented twice as often as any other value, right? And then I take that and I take its absolute value. And now that can range from 0 to +4. So it's a good array index. So once I do this, and I change that character C to the string C, quote, it does indeed print C16. And what can we learn from this one? Well, a bunch of things. The most important thing is math.abs does not guarantee a negative result. More generally, 2's complement can screw you. There's this odd man out, and integer.min value behaves strangely. So you should always be aware of it. It causes overflows, and the overflows are counterintuitive. Also, the mod operator is not a mod operator, it's a remainder operator. Its sign is the same as its numerator's sign, unless it happens to be 0. And the right way to translate a signed hash value to bucket, either you do the mod before the absolute value, or you simply discard the sign bit. And there's 2 ways to discard it. One is you shift everything to the right, throwing away the low order bit. The other is you mask it with basically not integer.min value. That's what this is, the complement of integer.min value, just thus throwing away the sign bit. Or if the array happens to be a power of 2 in length, you can simply use the low order bits and discard a whole bunch of high order bits. But that's a little bit dangerous. You have to know that the entropy is well distributed among the bits of your hash function to do that. So be careful when you're doing this. It's probably a premature optimization. All right, we have 2 more problems, and they're short. They're arithmetic. First one is division. See, it's called long division. These are cells dividing. And in fact, it's got a clever pun in the name, too. It's about division of longs, hence long division. We have 2 long constants. The first represents the number of milliseconds in a day, which is 24 hours per day times 60 minutes per hour times 60 seconds per minute times 1,000 millis per second. And by the way, the reason we're storing them in longs instead of ints is to prevent overflow, because this next value is actually pretty big. It's the number of microseconds in a day. And it looks just like the first one, except we add one more factor, which is 1,000 for 1,000 micros per milli. Then we divide the number of micros per day by the number of millis per day. So we divide the big one by the little one. And what does it print out? Well, all this junk should cancel, and it should just print out 1,000. And that actually makes sense, right? Because if you divide the number of micros per day by the number of millis per day, you get the number of micros per milli, which should be 1,000. So my question to you, does it print 5, 1,000, 5,000, or does it throw an exception? I'll give you a short time to think about that one. Maybe it's not a trick question. You never know. All right. Take 5 more seconds. Say again? It could be. You never know. All right. How many people go for choice A, 5? Got 5 of you. How convenient. Not really, by the way. It's actually 8, but I just wanted to say 5. How many people go for choice B, 1,000? Yeah, about 3/4 of you. This one's like too short to actually contain a trick, isn't it? How many people go for choice C, 5,000? A couple of you. 3 of you. And how many people say it throws an exception? 10 of you, and you're very enthusiastic. So I have to ask you, what exception does it throw? Well, what exception can division of an integer by an integer throw, or long by long? There's only one, divide by 0. And that's only true when the denominator is 0. Is this 0? That's just a silly answer. I'm sorry. No, I shouldn't make fun of anyone. But, and in fact, I put it there. And moreover, these are all hard problems. So what is the correct answer? 5. Well, yes, 5 is the correct answer. And why is 5 the correct answer? Because the computation does overflow. How could it overflow? We're storing the results in longs. That's 64 bits. How much can you store, roughly speaking, in 64 bits? Billions. That's like a big number. It's just gigantic. 2 to the 63 because they're signed. But anyway, it's just gigantic. So what's going on? Let's take another look. See, here's the problem. Yes, the long is big enough to hold the number of micros per day. But look how we're calculating it. This is an int times an int, which is an int, times an int, which is an int, times an int, times an int. And I'm sorry, but by the time we multiply by that last 1,000, we are above 2 billion, and we have overflowed the int. We compute the wrong value, and we store the wrong value into the long, which is big enough to hold the right value. The problem is that Java does not do target typing. It doesn't take the type of the variable into which the result is being stored into account when it is doing the computation. So, first question is, how could you possibly have guessed that? It's not a fair question if you couldn't have guessed the right answer. So let's go back and look at your choices. Well, here's the deal. When you overflow with one multiplication, is the answer going to be too big or too small? Too small. It's got to be too small. You overflowed, you wrapped, it's too small. So that rules out 5,000. We know it's not 1,000 because it overflowed, so it didn't calculate the correct value. And we know it didn't throw an exception, as we discussed before. So 5 is the only feasible answer, no matter how strange it seems. And how do we fix it? The way we fix it is we start these calculations off on the right foot. If we start out with a long value, then when we're multiplying a long by an int, the int is going to be converted. That's our old friend, the primitive widening conversion again. It's going to be converted up to a long. And when you do the whole computation in longs, there's no overflow because 64 bits is gigantic. And this one actually does print 1,000 as it ought. The last problem of the night. Oh, sorry, wait, I forgot the moral. It's the most important part. I'm sorry, I forgot the moral. So, when working with large numbers, watch out for overflow. It's a silent killer. By silent killer, I mean you don't get any warning. The wrong thing just happens. Even though it's a compile time constant in this case, it just does the wrong thing at runtime. So whenever you are working with very large numbers, err on the side of caution. Use a larger type. See, that's kind of a little typographical pun there. Larger type, get it? You might say I'm a font of wisdom. Yeah, sorry. All right, last one. Multiplication is complicated. Addition is easy. So this one is an addition problem. In fact, it's 2 addition problems. In the first one, we're adding 1, 2, 3, 4, 5. You notice that nice ascending sequence? And in this one, we have a descending sequence. 5, 4, 3, and so forth. And notice that when you're adding these ascending and descending sequences, 5 plus 1 is 6, 4 plus 2 is 6, and so forth. Shouldn't be too hard, right? And this is another one of those ascending, descending sequences, except the numbers are slightly different. So take a gander at this one for a moment, and then we'll talk about what it does. Oh my. I was so I'll tell people afterwards. But why? Why does chmod use these octal numbers? The answer is because machines used to have very small words, and in fact some of them had like 18-bit words, 6 groups of 3, and Unix was written in the 1970s, and that's when Unix picked up that particular bit of idiocy. So anyway. They have, yeah. In fact, they back in the old days, you could use variable length bytes, and this is why old codgers sometimes want you to say octet instead of byte, but I think they're full of it. A byte is 8 bits. Yeah. All right, and we are back. I wish we had a little bit more light, but so what we're going to do is I'm going to show you the possible choices here. All right, those are the choices, and they're basically kind of a regular array of choices. They're 17777 or 66666 for the first edition, and either 44444 or 43878 for the second edition. So you just have to sort of solve these two problems independently and then pick an answer accordingly. So I'll give you 10 seconds since you've already had a long time to think about it. All right, time is up, and we'll take the votes. So how many believe that this one is choice A, 17777, followed by 44444? La la la. I only see maybe a couple of you, 3 of you. 3 for choice A. How many people go for choice B? I see 4 of you. 4? 4. How many people go for choice C? I see about, I'm not 100% sure, but it looks like 5 over there and 5, 10, 15. I'm going to say maybe 15 to 20 for choice C. And how many people for choice D? Oh yeah, D is most of you. It's 80% of you. Well, nice try. It turns out the correct answer, yes, is choice B. And as for why, well, 2 things. First of all, the program doesn't say what you think it does. We're going to take another look at it in a moment. And second of all, leading zeros are not innocuous. So let's take another look. First, as to what the program actually says. Look very carefully at these figures. This is an acute angle, and that's a right angle. So what does Java do? What does Java do when you have an L at the end of an int constant? It's a long constant. So this is the long constant, 5,432. So we're adding like 5,000 to 12,000, and the answer we get's about 17,000. And before you get angry and like throw tomatoes at me and stuff, this one has a very important lesson, so hang on for that. The lesson is use a better font, and in fact, some machines will do that for you, some editors, but you can't depend on it. Honestly, Courier, which this is used in, this is Courier New, I guess. They look exactly like this. So as a practical matter, when you're looking at code listings, you cannot tell the difference between a 1 and an L. By the way, old typewriters did not have a 1 key. You simply used the L when you needed a 1. Strange but true. Anyway, so that's what's wrong with the first. And what about the second? Well, the problem here is this O. When you precede an int constant with an O, it is an octal constant. Yes. So what is octal? Octal is base 8. And why would anyone use octal?
Unix permissions.
Unix permissions, yes. So there's this one bit of weirdness from one operating system that comes from the 1970s. And why did they do that in the 1970s? Well, it has to do with what machine it was originally written for. It was written for these really tiny machines with 18-bit words. When a word is that small, every bit counts, and you just break it up into 6 groups of 3. But they don't have machines with 18-bit words anymore. They use powers of 2, so breaking them up into 3s isn't very useful anymore, is it? Octal is pretty much irrelevant to modern computer science, but unfortunately, when Java was being written, the rule was if something is in C, we'll do it the same way in Java unless there's a good reason to do otherwise. And in this case, there was a good reason to do otherwise. Octal was really already dead, but they just let this one slip by. So, how do we fix it? Well, duh. We change the L to a 1, and we take out the lowercase 0. And then it prints, I should have put what it prints here, but it prints 666, 666, and 555, 555, just like it ought. And what can we learn? This is the important part. First thing we can learn is always use an uppercase L for your long literals. Never use lowercase l. I have seen in many C++ programs a lot of this lowercase l and LL and stuff. That's garbage. It just confuses you. If you see this in a program, it's misleading. Who knows what the author intended? If you see this, it's clear. He wanted the long constant equal to 5,432. Similarly, never use a lone lowercase l as a variable name because it looks like 1. You'll confuse people. And finally, never precede an int literal with a 0 unless you actually want to express it in octal. That's rare. It's so rare that if you want to do that, you should have a comment in your program saying, this is an octal constant. Because otherwise, some helpful guy, like maybe this guy over here, when he's kind of modifying your program, putting in some sort of important change, will say, oh, look, there's all these like leading zeros that make it look like crap. We'll take them out. And if the numbers happen to be small, like between 0 and 7, no problem. It won't change their value. If they're bigger, you lose. So if you actually want it to be octal, say it, because otherwise it's not going to stay octal. And that brings us to the end of the regular part of our talk. So, to summarize, Java is still reasonably simple and elegant, though a lot less so than it used to be. And we're working on it, by the way. It's going to be even less so in the future. But for now, it's reasonably simple and elegant. It has a few sharp corners. Learn what they are and learn to avoid them. The best way to avoid them is to keep your programs short and simple. Because if you don't know what the program does, then it probably doesn't do what you want it to, right? Yes, use a good IDE. IDEs will find a lot of these things for you. Also, there's a program called FindBugs, and in fact, a plugin for a bunch of IDEs. How many people have heard of FindBugs? Oh, not a lot of you. You should know about FindBugs. FindBugs is a free open source program from Professor Bill Pugh and his former graduate student David Hovenmeyer from University of Maryland. You can download it, you can run it across class files. You don't even need the sources. And it finds bugs, and it tells you the line number of the bug and what the bug is. The fact that it works on class files is great because you can take closed source software. You can take somebody else's jar file, you can run it, and you can do a bug report where you give them the file and the line with the error, and it really freaks them out. They say, oh my God, how did you get your hands on our source file? And you say, I didn't, I just ran it through FindBugs. So check out FindBugs. And now, a word from our sponsors. If you enjoyed this talk, then you'll certainly enjoy this FindBook, which has 95 puzzles in it, and a whole bunch of optical illusions, and tons of fun. Do you all know what this is? In fact, it's a shameless plug. Yes. That's a shameless plug. All right, and now the last thing we have to do is give away the prizes. So there were 8 problems total, sort of honor system. Did anyone get all 8 problems right? These are very difficult. I would be shocked. No one ever says yes. Did anyone get 7 right? One person got 7 right. All right, come on down. You get a prize. Now, I have 2 books. So did anyone get 6 right? 6? 5? So the problem is there are 3 of you who got 5 right, and I only have 2 books. Yeah. So what we're going to do is I don't know. What's the fair way to do this? No, that would be wrong. Yeah, we could have a puzzle. No, everybody has to go. I'll tell you what. What I will do is I'll give both books to this gentleman who got 7 right. It's the only fair way to do it. So I apologize to the other 3 of you, but thank you all for coming. I hope you learned something useful. All right. You can sign up for you.